Hello everyone. So in this session we are gonna prepare for VLSI interviews. So from basics we will cover all basics from digital electronics and up to Verilog we will do. So what are the subjects that we are gonna watch are one is digital electronics, and then we are going to jump into EDC, electronic device and circuits, and parallelly we will also learn Verilog concepts, and then we will go for network theory. So these subjects are something that we need to prepare for VLSI interviews. So we will start digital electronics today. So every session we will learn some new topic or everything will be online. So let us prepare together now. Now for digital electronics we will start with number system. So we know there are basically four types of number system. One is decimal, and next is binary, and third one is octal, and next is hexadecimal. So these are the four types of number system that we are having. So we know that the decimal number system base is 10, binary number system base is 2, octal is 8, and hexadecimal is 16. So now we will understand each number system, and we will also understand conversations. We will learn conversations of one type of number system into another type of number system. Now let us start with binary number system. You know, binary number system is a number system with base 2, which means the maximum number that we are having is 0 to 1. So we are the numbers in binary number will only have 0 and 1. So if you want to find range of binary number system, then the range will be 0 to n minus 1. So n is the radix or base, radix or base. So this is binary number system. So now let us understand the binary number system and its weights. Now let us say I am having a binary number 10101. So let us say this is my binary number. Now what is the decimal equivalent of this number? So let us understand with decimal number system. So if I am asking, or if I am telling, so 254, so then that means it is 2 into, this is 10 power 0, 10 power 1 and 10 power 2. So that means this is 2 into 10 square plus 5 into 10 power 1 plus 4 into 10 power 0. So that will give me how much? 200 plus 50 plus 4, that is 254. Similarly, for binary number system also we will have same type. So this is my 2 power 0, 2 power 1, 2 power 2, 2 power 3 and 2 power 4, right? Now let us calculate. So this is 1 into 2 power 4 plus 0 into 2 power 3 plus 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. So that means 1 into 2 power 4, that is 16, plus 1 into 2 power 2, that is 4, plus 1 into 2 power 0, that is 1. So 16 plus 4 plus this is 21. So 10101 means it is 21 in decimal number. So that is how we will convert binary number into decimal number. So now let us say if I am given 10101.11, then how to find the decimal equivalent for this one? So for this one it is same, we will follow, that is 1 into 2 power 4 plus 0 into 2 power 3 plus 1 into 2 power 2 plus 0 into 2 power 1 plus 1 into 2 power 0. Then we will take this one as 2 power minus 1 and this one as 2 power minus 2. That is simple. That is 2. Right, 1 into 2 power minus 1 plus 1 into 2 power minus 2. So this means that 16 plus 4 plus 1 plus 1 2 power minus means 1 into 1 by 2 plus 1 into 1 by 4. That gives me 21 plus 1 by 2 is 0.5 and 1 by 4 is 0.25. So my decimal equivalent is 21.75. So this is the decimal equivalent for this one. Now we will understand the decimal equivalent. So what do we call these? We call these as weights. Weight of the position. So the first position from right side is the lowest of position. So we will call this one as LSP, which means least significant bit, and we will call this one as MSB, which means most significant bit, which means most significant means I am having highest weight, and this is lowest weight. So I think you understood MSB and LSB. Now what are the different terminologies that we will use for this? Now let us say I am having group of 4 bits. Then I will call it group of 4 bits, I will call as one nibble. Similarly, if I am having 8 bits, then it is known as 1 byte. So you probably would have listened byte. Byte means 8 bits. Similarly for 16 bits, we will call it as word, and for 32 bits we'll call it as double word. So these are the terminologies that we will come across in binary number system. So we have understood the binary to decimal conversion. Now let us try to understand decimal to binary conversion. So for decimal, here we will learn decimal to binary. So here, let us say I am having 13 base 10. That gives me how much? You can write as, if you are writing, then we will solve. So we will take this method. So I am writing 13. Then I will divide by 2. So 2 6 times 12, and I am having remainder 1. Similarly to 3 times remainder 0. 2 1 time, 1s are 2, remaining remainder 1. So right here the decimal number is, we need to write from bottom to top. My decimal number is 1101 is 2. So I can write this 13 as in 1101 in decimal number system. So that is how you will convert one type of decimal system into another decimal system. That is, here we are learning decimal to binary. Now let us try to understand another example. Here let us say I am having in decimal form 256 point like 25.625. So this is the question. So this is in decimal number system, and find the binary equivalent of this number. So here what I will have, same method we will use for, first we will solve for positive decimal, and then we will come to the day after decimal. So here I will have relate 25. So 2 12s are 24, remainder is 1. 2 6 are 12, remainder is 0. 2 3s are 6, remainder 0. 2 1s are 2, that gives me remainder 1. So I am getting here 11001. First I will write 11001 here. 1101, sorry, 001, right? 11001. So this is 25. Now we need to find for 0.65. So now in order to find 0.65, so here we will multiply by 2. So then how much we will get? 1.25. So the after 1, how much is it that we will take? This one we will have 0.25 into 2. That will give us 0.5. So we will 0.5 into 2, and you will get 1.00. So if you multiply 0.0 into 2, and again you will get 0. So what we can observe here, you need to write these one. So my here it will be 1010. So 25.625 I can write as 11001.1010 in decimal form. Now we will learn about decimal to octal. So now we will learn decimal to octal. So we know, let us take understand with an example. I am having 112 of decimal number, 112 decimal number. Now I need to find its equivalent in octal number system. So how we calculated by a decimal to binary? Here we are taking 2, but for octal base is 8. So here we will take 8. So same method, but we will take base as 8. So I am having 112. So if I am dividing by 8, so then that will give me how much? 8 ones are 32, 4. So my remainder is 0, 8, 1, and remainder is how much? 8 ones are 8 plus 6. So 6 is my remainder. So 160. So my equivalent is 160. So 112 in decimal means it is 160 in octal number system. Similarly, now let us understand with another example. We will take same 25.625. Now we will find its octal equivalent. Now first we will find for 25. 8, 3 is 24, remainder is 1, 31. So we are getting 31. So for 25 it is 35, sorry 31. Now we will find for 0.65. So for there we are multiplying with 2. Now here we will multiply with 8. 0.625 into 8. That gives me how much? 8 5s are 40. 40. These are 16, 20. 8 6 are 40, 52. 5.2. 0.625 if I am not wrong. Sorry, it is 5, not 5.2. So here 0.00 into 8. That will give me how much? 0. So my answer is 0.50, or you can simply write 31.5 in octal number system. Similarly, let us find for another number. We'll practice for another number. Two 048 base 10. So that will provide some octal number. Now we need to find the octal number for 2048. So first I will draw this one. So now 2048 divided by 1s are 44, 5s are 40, right? So 4, 48, 6, 156. So this is remainder 0 and 8. 1s are 56. 56 will how much? It's 256. Sorry. So then we will get 32. How much times 30? Sorry, 32. Remainder is 0 and 4 remainder is 0. So you get 4000. So 2048 in decimal will give me 400 in octal. So that is another one example. Now let us understand with another example here. So here we will take 82.250 base 10. Now I want it base octal. Oh, 82, 8, 10, 2, 8, 1, 2. So 120. So 82 is 120. Now we need to find for 0.250. So 0.25 into 8. That will give me how much? 2. And 2.00. So 0.00 into 8, it will be 0.00. So 0.2. So this is base 8. So that is the answer. Now we will find our decimal to hexadecimal. So same procedure we will do. Now let us say, for example, I am having 254 base 10. Then what is my equivalent in hexadecimal? So in order to convert this one, we will first understand hexadecimal. Hexadecimal means we know base 16. So what is the maximum number that we will have? 0 to 16 minus 1. So that is 0 to 15 is my range. So 0 to 15 is my range. But we will only take up to 0 to 9. And from 10 onwards we will take A. And my 11 will be B. And my 12 will be C. 13 will be D. 14 will be E. And 15 will be F. So this is how we will write. So up to 09 we will write normal 9 digits, and then from 10 onwards we will write A, B, C, D, E and F. Now let us understand a problem with this one. If I am given 254 base 10, I think yeah. So take 54 base 10. In hexadecimal, what you will get? 254 16. 16 ones 94. So 94 means how much? then you will get 15 as remainder, and then you need so 16, this is 15 is remainder. So this is 14. So you will get FE. Now let us try to understand with another example. So let us understand for decimal number 25.625. So what is the decimal equivalent of 25 point, sorry, hexadecimal equivalent of 25.625? Now 25 we will solve, take 16, 1 and is 9. So we will get 19. 19 point. Now point 0.625 into 16. So you will get equal to 10. You will get 10.00. So the 0.00 into 16 you will get 0.0. So you will write 10. 10 means A. So 19.A base 16. So that is the answer. Now let us find for another question. To say 27.4 in base to hexadecimal 16. So then simply 27, 16, 1. So how much is the difference? 11. So 11 means how much? B. So 27 is 1B point. So now we need to find for point 4. So what we need to do? Then we will have point 4 into 16. 0.4 into 16. Then you will get 6.4. And again you need to take 0.4 into 16. So you again get 6.4. So then you will get here 6 bar. 1B on 6 bar in hexadecimal. Now let us try to understand. Next topic is, we know binary to decimal, we know octal to decimal, hexadecimal to decimal. Octal to binary and hexadecimal to binary also we know. Now let us go into binary addition and binary subtraction. So now let us understand binary addition. So if I am giving you 1 1 0, 1 1 0 and 1 0 1. So I need to add these two numbers. So if I am saying that this topic is binary addition, so we are adding two binary numbers. So what is the way this means? This is equal to, so this implies to 1 into 2 power 2 plus 1 into 2 power 1 plus 0 into 2 power 0. Similarly, this is 1 into 2 power 2 plus 1 into, sorry, 0 into 2 power 1 plus 1 into 2 power 0. Now we need to add this one. So 0 and 1 is 1. 1 and 0 is 1. So 1 and 1 is how much? So that will generate sum is 0, carry equal to 1. So now let us understand this one. So if I am adding, let us say 9 plus 1. So then I am getting 0 and carry is 1. So that is how we are getting 10, right? So we are not getting directly, we will get 0 and 1. So from what we can understand from this one is, for binary addition, let us write two separate columns for sum and carry. And now let us say I am taking sum of 0 plus 0, then my sum will be 0 and carry is equal to 0. Or if I am taking 1 plus 0 or 0 plus 1, then my sum will be 1, carry will be 0. But if I am taking 1 plus 1, then that means this is 1, sorry, sum is 0, carry is 1. So that is how we will do binary addition. Now let us go into R's complement. First we will find R's complement and then we will understand 1's complement, 2's complement and different number of complements. Now let us say R's complement. So why do we use this R's complement? So we use this R's complement for simplifying subtractions in digital devices. Now for, let us say, to find complement, there are two types of complement. One we will call it as R's complement and another one is known as R minus 1's complement. First let us understand R's complement. So another name for R's complement is radix complement. And R minus 1 complement is known as diminished radix complement. So I think you understood what we are calling R's complement and R minus 1's complement. Now let us try to understand R's complement here. So now if I am saying R's complement, let us say I need to find complement of 7 base 10. Then simply what I need to do is, there is a formula for this one. Here my n number is 7 and my number of digits in this one is, here I am only having one digit and my radix is 10. So simply what I do is, in order to find r's complement, the formula is r power n minus n. So this is the formula. Now if we substitute in this formula, then you will get here r power n, that is 10 power n is 1 and minus 7. So you will get 3. Complement of 7 base 10 is 3. Now similarly, I am giving you another question. Let us say n is equal to 5690. Then determine tens complement. So if this is my question, now simply I will substitute in the formula. So what is my formula? R power n minus n. So here what is my n is 5690. My n is equal to 4. Number of digits are 4 and my radix is 10. Now I will substitute in this formula. So 10 power 4 minus 5690. Simply that is 10,000 minus 5690. That will give me 1 3 4 4 3 1 0. So that is my r's complement. Now if I am asking another simple question, I am giving. If I am asking n is equal to 1101 and I am asking to find whose complement. So then it will be, my n is this one, my r is 2, my small n is 4. So if I am substituting in this formula, then that is 2 power 4 minus 1101. So 16 minus 1101. So here my 1101 is in how, what you call, it is in decimal number, right? So if I am converting this into decimal, 16 into decimal, then I will get how much? If I am converting 16 into decimal, 1 2 3 4. So this is my decimal number in binary, my 16 in binary number. So I will subtract two binary numbers, then that will give me how much? 0 0 0 1 1. So that is equal to 1. So this is my 2's complement for given number. Now let us go for r minus 1 complement. Let me check if my voice is audible or not. 1 second. Okay, my voice is audible. Now let us find r minus 1's complement. Let us learn r minus 1's complement. So let us say if I am giving r is equal to 10 and I am asking to find 9's complement, then simply I will find 10's complement and I will do minus 1, then I will get 9's complement, right? Similarly, for r is equal to 8, I will do r minus 1, then I will find 8 complement first and then I will get 7's complement. So this is one way of calculating. So by this what we can write? The formula r minus 1's complement formula. We are getting r minus 1. That means r minus 1. What is the formula for r? R power n minus n. So this is for r and I will subtract 1 from this one. Then I will get r minus 1 complement, or simply you can write r's complement minus 1. So this is the formula to find r minus 1 complement. Now let us try to understand this one. Now let us solve with example. Here what is the example I am having? Okay, now so if I am asking 7's complement of octal number 5674. Now what I will do is, so since I am given octal number, I will find with taking r is equal to 1. Now first what I need to do, I need to find for r 8, right? So here then 8 power number of digits is 4 minus 5674. So if I am finding 8 power 4, this is what, and I need to do minus 1. This 5764 is 8 over 4 is 4096. This is in decimal, right? Hmm. 4096 base 10 and 5674 minus 1. So if I am converting this one into octal, then I will get 777 and my octal, and now finding 7's complement, right? 5674. Then that will give me 2103. And now let us find another way of solving this one. If I am asked to find 8's complement, of 5674. Now what I will do is I can directly use that formula, but in order to make understand, we will find 7's complement minus 1. So what is the 7's complement of 5674? If you subtract this one, 777 5674, I will get this one 73012. So this is 7's complement, and I will do plus 1, then I will get 2104. So this is 8's complement. This is 7's complement. So if I, in order to find r minus 1 complement, if we simply find subtract every digit by that one, then you will get that one. Now let us say if I am asking you to find, let us learn, okay, now let us learn 1's complement and 2's complement. So in order to find 1's complement, what I will do is, let us say I am having 1 I am having digit 1010 base 2. So and I need to find, and I will simply subtract from this one, then I will get 1010. So 0101 is my 1's complement. So in order to find 2's complement, I will add this one, and 1 is some 0 carry 110. So 0110 is my 2's complement. So this is my 1's complement, and this is my 2's complement. Okay, now let us find. If I am asking you to find obtain 2's complement of 10111010 is 2. Then in order to find 2's complement, or what I will do, I will find 1's complement, and then I will do this one. So in order to find 1's complement, so when if we are subtracting this from 11111, then that will equal to the reciprocal of this one. So 1's complement is always the reciprocal of given binary number. So here this is my binary number. My reciprocal is 010000101. So this is my 1's complement, and simply I will add 1. Then I will get 2's complement, 1101 and then 100010. Similarly, if I am asking you to find 2's complement of 1101, 0 0 1 1. Now in order to find this one, what I need to do? I need to find ones complement. So ones complement is 0 0 1 1 0 0 0. Now I will simply add 1 to this one. 1 0 0 1 1 0 0. Now from this we can understand, we can yeah, we can find an, by in this observation we can find an easy way to do the shortcut method. Now first we need to in order to find the two's complement, what I need to do is first we need to shortcut for two's complement. So there is an easy shortcut method. Instead of finding one's complement and doing all that, first write down the number, and then what you need to do is from starting from LSB, that is from right hand side, copy all the zeros, and then first, and then if you are getting one, then copy the first one, and then write complement of remaining bits. So let us say we will solve this one. I will duplicate or I will up this part. So let us find in one line I will get. So here my first step is to write down the number. Now I am writing my number 101111010. And next what I need to do, starting from LSB, copy all the zeros. And here is only one LSB and I need to copy first one. And then I need to complement the remaining bit similarly, and here 1 0 0 0 1 0. So this is my two's complement. So this and this is equal. Instead of doing this reciprocal and writing first finding reciprocal and adding one, directly what I will copy first number of zeros and then I will do the reciprocal. Now let us understand with simple question. Now let us say I am asking you to find complement of 1011 1000 basically. So if I am asking to complement, write the two's complement, simply what I will copy all the zeros from LSB, first one, and then reciprocate 0 0 1 0. So this is my two's complement. That's all. You can write directly instead of solving all those one. Now let us understand another important topic of digital electronics, that is data representation. There are two ways of representing data. One we call as magnitude, another known as complement. And we can further classify this magnitude. So in magnitude we can write unsigned and sign. And for complement, we have 1's complement and 2's complement. Now let us understand here what is unsigned. So for unsigned, we will only have positive binary. So for signed integer, we have positive and negative binary. For 1's complement also we will have positive and negative, and for 2's complement also we will have positive and negative. So in all four representations, only in unsigned is having positive, unsigned only will not have negative number, but all other will have positive. So what we can understand, all positives can be will be represented in same way, but the ways of representing negative number will only change. Now let us understand unsigned magnitude. So for unsigned magnitude, what I have said, we will only have positive. So if I want to represent 6, then it will be 110. So if I want to represent -6, then it is not possible. We can write is cannot be represented. So, but for unsigned, for signed magnitude, we can write both positive and negative. Similarly, if I am writing 8, we will write as 100. But -8 we cannot write in unsigned magnitude. Now let us understand signed magnitude with the same examples. So for signed magnitude, if I am writing +6, what I have said, for positive everything is same. For +6 we will have 110. For -6, what we will have, we will add one extra bit to represent the negative sign. So we will have 0 for positive and 1 for negative. So that is how we differentiate between positive and negative number. So this bit we call them as sign bit. This will represent the sign which is positive or negative. Now let us understand the range of sign magnitude. Now let us understand the range of sign magnitude. Now so the range of sign magnitude is -2 power n minus 1 minus 1 to plus 2 power n minus 1 minus 1. Sorry, this is not 2 power n minus 1, it is 2 power n minus 1. So positive side it is same, 2 power n minus 1, but for negative side it will change. So let us say for n is equal to 4, we will find this one. So for n is equal to 4, then that will be 2 power 3 minus 1 to 2 power 4 minus 1. That is, here 2 power 3 is 8, 8 minus 7 to 15. sorry, 2 power 3, 2 power 4 is 16, 16 minus 1, 7, sorry. Here it is 2, n minus 1, n minus 1. So here it is plus 7. So from minus 7 to 7. So to represent plus 13, we will write 0, 1, 1, 0, 1. But to represent minus 13, we will write 1, 1, 0, 1 and another one to represent the negative. Now let us understand. Shall we go to Boolean theorems now? I think this is sufficient for number systems. Now let us go into Boolean theorems, one of the most important topic. Now we are entering basics of digital electronics. So we will take 1 minute break here and then we will continue. Okay, now let us start Boolean theorems. So there are, first we will understand different Boolean theorems based upon operation. First we will, one side we will write Boolean theorems related to OR operation, and one side we will write related to AND operation. So what are the Boolean theorems that are related to OR operation here? So for our OR operation, we will have A plus 0, sorry, A or 0, then my output will be A. Similarly for A or 1, my output will be 1. And A or A bar, then my output will be 1. And A or A, then also my output will be A. So now let us understand. Let us take different values of A and substitute. If I am taking A is equal to 1, then my output will be 1. If I am taking 0, then my output will be 0. So here my output is only A. Similarly, if I am taking A plus A or 1, then that will give me, let us take A is equal to 0. 0 plus 1 will give me 0. So, sorry, 1. And 1 plus 1, 1 or 1 will also give me 1. Similarly, if A or A bar, that means 0 or 1, that will be 1, or 1 or 0, that will also be 1. If A 0 or 0, that is 0, 1 or 1, that is 1. So that is how we will understand Boolean theorems related to R. Now coming to Boolean theorems related to AND operation. then A and 0, that will give me 0, A and 1, that will give me A, and A, that will give me A, and A bar will give me 0. So now let us understand this one by substituting different values. If I am taking A is equal to 0, A is equal to 0, then is 0 into 0, that will be 0. And if I am taking A is equal to 1 and 0, that will also be 0. Similarly, if A and 1, so 0 and 1, that is 0, and 1 and 1 is 1. So here my A is only output. So A and 1 is AND. Similarly here A and A, 0 and 0 is 0, 1 and 1 is 1. Here also what is my A, that is only being replicated as output. Now A and A bar 0 and complement if 0 is 1, that is 0, and 1 I am taking as A, then complement is 0, then I will have 0. So from these derivations what we can draw one conclusion. So what is that conclusion? 1 plus anything, 1 or anything. So if you are seeing 1 in your equation, then that will always be equal to 1. See, if you represent 1 plus 0 plus 0 plus or 1, then you will always get 1. So that is the meaning. And while coming to operations related to AND, 0 and anything will be equal to 0. So these are the operations, Boolean theorems related to AND and OR operations. Now let us understand some important Boolean theorems. Let us say I am having A of B plus C. Then that means that will be equal to AB plus AC. So what we can write here? Here this is the distributive law, and what is the distributive law here stating? Here my and operation is distributing over OR. So here my AND is distributing over OR, and is distributed over OR. Similarly, if I am given A or B and C, then it will be A or B and A or C. Here my OR is being distributed. OR is distributed over AND. So this is the distributive law in Boolean laws. Now let us understand another important one. Now let us say I am having A plus A bar B. When you try to solve this one, you will get A into A bar. When apply distributive law, then that will be A B. So A into A bar is A and A bar is, we have learned that it is 0. 0 plus AB. We will get A B. Now I am having A bar plus AB. Then I will have A bar B. Now when we observe carefully here, my A here is being replicated and my A bar is being eliminated. So here also my A bar is I am getting, and I am having my A is being eliminated. So that is one thing that you need to observe. If you are observing this type of equation while performing simplification of problems, you every time you don't need to write this one every time. You can simply write a plus a bar b is equal to ab. Okay, now let us understand with same example. If I am having a plus a bar bc, then that will be equal to, sorry, I've done one mistake. If I'm having a plus a bar b, right? So that will be equal to a plus a bar. So I have distributed wrong, and that will be a plus b. So here that will be a plus a bar is 1 and a plus b. So here it is a plus b. And if I am having a bar plus ab, then I will have a bar plus b. Similarly, if I am having a bar plus a bc, then I will have a bar plus bc. So that is what trying to say. Now there is another important theorem in digital electronics, that is called redundancy theorem. What my redundancy theorem we will states is, we will understand with the example. Let us say I am having AB plus A bar C plus BC. So if this is my equation, what my redundancy theorem states is, first try to, in an equation, try to find terms where I am having one as normal term and one as complement term. So here I am having A as normal and here I am having A bar as complement. So what I need to find is the remaining terms of this equation. So here I am having B and C must be available as the another term. Then that for that type of equation, this will become my redundant term. This then you need to simply eliminate it, and my equation will be AB plus A bar C. So that is my output equation. Similarly, if I am given A bar B plus ACD plus BCD, now same verify the same. So here I am having A bar and here I am having A and here I am having B, and my remaining terms are BCD, and my having in 8 and 10 terms. So this my output will be A bar B plus ACD. So simple. So that is how you will find the redundant terms and eliminate the extra terms that you don't need. So this is redundancy theorem. And then next we will have De Morgan's law. Or De Morgan's theorem or law, you can call it anything. So for this there is an equation, title line for this one, that is break the line and change the sign. So this is the title line for De Morgan's theorem. Wherever you see a bar, try to split it, and if I split the bar, and if you are seeing or, then convert into and. If you are having and, then you will convert into or. Now let us try to understand that with an example. If I am having A plus B bar, then simply I need to break the line A bar B bar. I am breaking, and I'm changing the sign. If I'm having operation or operation, then I will give AND operation, that will be A bar and B bar. Similarly, if I'm having A B bar, then I will break the line and change the sign, that will be A bar plus or B bar. Now let us find for this one A bar B bar plus CD whole bar. Now apply De Morgan's theorem for this equation. So when you apply De Morgan's theorem for this equation, first we need to break the line. So A bar B bar plus CD bar. Now again break the line and change the sign here. You will get A bar plus C bar plus D bar. That will be equal to A plus B. Sorry, here it is not R. Here it is C bar plus D bar. So that is your output. If I are given for this one, your simplification is this one. So that is how you will apply De Morgan's theorem. By apply until now we have learned different laws, right? Now we will try to implement in a question. So here is one question that I am having A plus BC plus A bar C. So for this type of question, what I need to do? First, we will verify if redundancy is possible. Yes, A and A bar are there. Here I am having if only C would have been there, then if B would have not been there, then the redundancy theorem would have been applicable. For this question, redundancy is not applicable. Now try to solve this equation. What we will do? We've learned one equation, right? A bar C plus BC. So if A plus A bar C, that means what I can write? I can write as A plus C plus BC. So now in these two terms, I will take C as common. C of 1 plus B. 1 plus anything is 1. So my answer is A plus C. I think you have understood this one. If you are having doubt, please ask, I will explain again. Similarly, we will solve another question. We are having A bar B plus AC plus B bar C. So this is the question. Now in order to solve this question, what we need to do? First I will draw a line here. So in order to do this. Now here I am having, let us see if redundancy theorem is applicable. Here I am having A bar and A. Here I am BC. If BC would have been there, then the redundancy would have been applicable. And another is B and B bar. So here it is A bar and C. If this have been bar, then redundancy would have been applicable. But here redundancy is not applicable. Now let us try to solve this question. First we will write A bar B as it is, and we will take C as common in this one. Then this will be A plus B bar. Now let us try to apply De Morgan's theorem for this question. Let us take A bar B as X, and then if I find to do the X bar A bar B whole bar, and here you apply De Morgan's theorem, break the line and change the sign. So here it will be A plus B bar. So A plus B bar. So X bar is equal to this one. So this one we can write as X C of into X bar, or you can write X plus X bar C. So the same concept that we have used here, we will use for this one. So X plus X bar C will give me X plus C. That means X is my A bar B plus C. So this is my answer. So I think you have understood. If you are having any doubt, please let me know. I will explain on that. Now let us understand another important theorem, but with an example we will understand. Let us say I am having a b bar of a bar b plus b bar c plus a b bar d plus a b bar d bar, and we are having whole bar. Okay. Now let us try to solve this question. So in order to solve this question, I will say one formula that we are having, that is, if we are having P into P plus anything, then my answer will be equal to P. So this is one important formula in this one, in Boolean theorem. So we will try to convert this one into this one. So first we will keep the whole complement side, and we will only take the terms in it. Now I will write the terms here, that is A. I will write in another color. A b bar of a bar b plus b bar c plus a b bar d plus a b bar d bar. So this is my, I am eliminating my whole complement. Now let us try to understand. Let us try to bring this one into this one, p into p plus anything. Now I need to make a b bar. Now let us say if there is anywhere a b bar, here a bar b is there, so not applicable. So b bar c is not there. And here I am having a bar b bar, and this one I am having a bar b bar, but I am having d and d bar. So we will try to eliminate d there. So how we will eliminate d? A b bar of a bar b plus b bar c plus a b bar I am taking common, and d plus d bar. So 1 0 plus 1, so d plus d bar is 1, right? Now I can write a b bar. So here a b bar will be there, and I am rearranging it, and I will a bar b plus d bar c. So here p and p plus anything, so my answer will be a b bar. So this is how you will simplify your Boolean problems. Yeah, every time you do not solve this whole and get one, simply you can use this formula and you can get the final answer. So this is how Boolean laws will help you in solving problems. Now let us understand another important concept. For VLSI interviews, I think duality is not that much important, duality theorem, but we will just cover on top. What does duality theorem states? So my duality theorem states that if in an Boolean expression, if you are replacing AND by OR, so AND is replacing by OR, or OR is being replaced by and NOT is being replaced by NOT, then the expression that we are getting also will also be true. Now let us understand here. I am having A plus A bar B. So this will be equal to, I will interchange, replace AND by OR and OR by AND. So here I will have A and A bar or B. So that will be equal to A and A bar plus A and B. A into A bar is 0, so you will get A, B. So this is equal to this one. A plus A bar B is equal to AB. So that is the duality theorem. So every time the function and the dual function of it may not be same, but this expression and this expression will always be true. So that is what duality theorem states it. And let us also find duality for remaining gates. If I am having NAND operation and I can replace with NOR and NOR with NAND. So what we can write, NAND is dual of NOR and NOR is dual of NAND. Similarly, XOR is dual of XNOR and XNOR is dual of XOR. So we've got and uh, and not is dual of not itself. So that is the concept. Now let us understand very clearly that f, let us say f is a function, f of a or b is some function. This may not always be equal to fd of b. Sometimes it may be equal to dual of ab, but every time it will not, f of ab will not be same with the dual function of itself. And some people will understand f complement of b is equal to ab. So these are possible cases, but every time these are not right. So what we can say is sometimes a function of ab will be dual function of ab, both will be same. Sometimes complement of ab will be equal to ab. Sometimes there will be no relation between f of ab and dual of ab and f complement of ab. Sometimes there will not be any relation, but the duality theorem exists there, but you will not always find the same term. So you need to understand this one. You will many of you will have misconception for this, so try to understand. Now let us we will solve one problem and understand that one. So let's here f of ab I am giving as a plus b bar into a bar plus b bar. Then find fd dual of a of b function and complement of the function. So find these two. We need to find fd. Fd means dual function and as well as the complement function. Now we will here we will find dual function and here we will find complement of the function. So what does my duality theorem states? A plus b bar, that means I can write a into b plus a bar into b bar. So that is what my duality theorem said. I will take b bar as common, then that will get a plus a bar, and a plus a bar is 1, so it will be b bar. B bar is my answer. Now we will find complement of f of ab. So what we need to find? ab is equal to a plus b bar into a bar plus b bar whole bar. So that will be equal to a bar into b. So we are not applying duality theorem, but we are applying De Morgan's law. So and this will be A into B. Now if I am taking B as common, then it will be B plus A into A bar. That will be 0 B. So my answer is B. So here we can observe FP of A of B is not equal to F complement of A of B. So that is why I am giving this question in order to understand that duality and complement are not same. But in some cases they can be same, but it is not always true that dual of the function is not always the complement of the function. Correct? Okay, now what is the next concept that we need to understand? Finally, we are coming to gates, concept of logic gates. Logic gates. There are three types of logic gates. And one type of gate is known as basic gates, universal gates, and another are arithmetic gates. So in basic gates we will get AND, or not. In universal gate we will get NAND and NOR. In arithmetic gates we will get XOR and XNOR. So these are the different types of gates. So now let us learn about basic gates. So initially we will learn about AND gate. So the symbol for AND gate is so this symbol we call it as AND. We will have two inputs, let us say A and B, and we will have one output Y. So this is AND gate. So output of AND is A dot B. So now let us draw the truth table of AND gate. So here I am having A, B, and output Y. So what are the combination? So in order to understand logic, if I am, we will have for gates. If I am having number of, where can I write this one? I will write here. Total possible combination is will equal to 2 power n. So where my n is equal to number of input. So you need to remember this one. I know you already know this one. So here I am having 0, 0, 0, 1, 1, 0, 1, 1. So these are the combinations here. So we are having two inputs. So 2 square, that is 4. We got all 4 combinations, right? So in what does my AND gate suggest? Simply, it is you can say multiplication, or you can say you cannot directly say multiplication. But what AND gate is implied is, if I am having both inputs as 1, then only my output will be 1. Or you can say, if my both switches are on, then my output will only be on. So this will represent, my AND will represent serial connection. So if one is on and other is off, then it will be 0. Either only if both of my inputs are on, then my output will be on. So this AND gate represents serial connection. Now how we will say? Let us say I am having one switch. Sorry. So this is my representation for AND gate. So this is my bulb. So this is bulb. So bulb will glow only when both of these switches are on. Now let us understand the truth table. Now let us say A is equal to 0, B is equal to 0, which means let us say 0 is equal to off state, 1 is equal to on state. 1 is equal to on state. So now if I am taking A is equal to 0, then that means both are in outputs. That means both are open. Then there will be no flow here. So my bulb will not go. So my output will also be 0. If I am taking A is equal to 0 and B is equal to 1, I am closing this one. But my current should flow from here, no, but my current will not flow here. So my output will be 0. If I am having A is equal to 1, B is equal to 0. If I am this is open and this is closed, current will come from here to here, but it will not flow from here to here. So my output will be 0 again. So if I am having A is equal to 1, B is equal to 1, then my both switches will close, then my bulb will glow. So here my output will. So this is AND gate. So if you are asking, if they are asking to explain AND gate with an example, you can simply draw this circuit and explain. Now let us understand OR gate. The representation of OR gate is simply this one. A, B and Y. Now we will draw table. Zero, 1, 1, 0. So these are my possible combination. So my output equation is Y is equal to A or B. So this represents parallel connection. Now let us understand with the circuit with the same example. So this represents parallel circuit. So take this as ideal circuit. Don't ask me why there is no resistance in it. Now this is A and this is B. Let us say backward. Now my A is 0, B is 0. Then my output is my here it will not pass from either of the switches, so my output will be 0. So then if I am saying A is equal to 0, B is equal to 1. So I am closing this one. So the current will pass from this and this will another. So my output will be high. Output is high. Now I am taking A is equal to 1 and B is equal to 0. Then this is open and this is closed. So I will have current path from this end. So my output will be 1. So even if I am taking A is equal to, I am closing both the switches, the current will flow from both the switches. So my output will be high. So this is the OR. Here only if my both the switches are off, my output is low. If either of my switch is on, then my output is on. So that is the OR. Now let us understand NOT gate. What is the representation of NOT gate? This is a NOT representation, or simply you can represent like this also. So what my NOT gate suggests, A will have only one input, A and Y. A and Y. If my output is 0, my output is if my input is 0, my output will be 1, and my output is 0, then my input will be 0. So this is my NOT gate. I think you understood. So NOT gate is also known as inverting buffer. So this is one important term. If they will ask what is the another name for NOT gate, then we can simply say it is also known as inverting buffer. Okay, we will learn multivibrators afterwards. Now what we will understand is enable and disable input of and or. Shall we learn those? Please answer if you want to learn enable and disable input of and or. Since there is no response, I am saying yes. I'm taking it as no. Now we will go into XOR and XNOR. Now we will go into arithmetic gates. So what are my arithmetic gates? Those are XOR and XNOR. Now let us understand XOR. The representation of XOR is so this is the symbol of XOR, right? My output equation for XOR is Y is equal to A bar B plus A B bar. Now let us try to understand this one. or simply we will write A XOR B. And XOR is known as OR detector or event generator. Now, what are the properties of XOR gate? We will learn this. So, what are the properties of XOR gate? If I am writing A XOR A, then that will be equal to 0. And A XOR A bar, that will be equal to 1. A XOR 0. So, if my one input is 0, then my it will depend on another input. So, A XOR 1 will always equal to A bar. And A XOR A bar, that will be equal to 0. And A bar XOR 0, that will be equal to A bar. So A bar XOR 1 will equal to A, and A bar XOR A whole bar will equal to 1 bar to 0. Now let us try to understand this one. So if I am saying A XOR A XOR A, that means let us say take A is equal to 0, then it will be 0 into 0 bar plus 0 bar into 0. That will give me 0 only. So that is why here we are having 0. And next, if you are having A XOR A bar, A XOR A bar means what? One is A, if I am taking A is equal to 0, then B will be A bar that equal to 1. So 0 into 1 bar plus 0 bar into 1. So that will give me 1. That is the equation. I think you understood this one. Similarly, if you substitute in this output equation of, if you are substituting in this equation, then you will be able to find all the values. Now, there is one important concept of enable and disable input of XOR. I will not XOR and XNOR. We will learn about NAND and NOR XOR. Let me check. I think it is meant. We will learn about enable and disable inputs in NAND gate only. Now let us learn about XNOR. So what is the sign for XNOR? So this is XNOR. Two inputs and output A, B. So we did not write truth table for XNOR. It's funny thing. Yes, we will draw truth table here. 0, 0, 0, 1, 1, 0, 1, 1. So what is my XOR output? 0, 0 will give me 0. Substitute here. 0 and 1 will give me 1. 1 and 0 will give me 1. So when you observe this truth table here, my output is high when I'm having odd number of ones. So that is why we call this as odd detector. Now let us learn for XNOR. XNOR equation, output equation. Y is equal to AB plus A bar into B bar, or you can simply write A XNOR B. Now let us draw truth table. A, sorry, okay. Now A XNOR B. Now what are the total number of possible input combinations? 0, 0, 0, 1, 1, 0, 1, 1. Now let us solve with the equation. Now taking A is equal to 0, B is equal to 0. Then Y is equal to 0 into 0 plus 0 bar into 0 bar. So that will equal to 0 plus 1. That is equal to 1. So my 0 into 0 bar is 1. Now A is equal to 0, B is equal to 1. So Y is equal to 0 into 1 plus 0 bar into 1 bar. That will be equal to 0. So this will be 0. A will be 1, B is equal to 0. Output will be 1 into 0, 0. And 1 bar into 1 bar is 0, 0 bar is 1. So again you will have 0. I am having A 1, B 1. Output is equal to 1 into 1 plus 1 bar into 1 bar. We have 1 as output. So when you observe here, here we are having 1 for even number of bits. So if this one we will call XNOR as event detector. Now let us understand one important topic. Before that, we will go into properties of XNOR and then we will go. So, what are the properties of XNOR? That is A XNOR A is equal to 1. A XNOR A bar. If you are having two different, then we are having 0. A XNOR 1 equal to A. And similarly, A XNOR 0 is equal to A bar. So what we can say, we will understand one concept in for XOR and XNOR. Now let us say I am having XOR gate. So let us take this one as 1 and I will take this as constant. This is A and I will take 1 as constant. So now let us try what we are getting. So A XOR 1 is always A bar. So it is acting as inverting buffer. Now let us try and take this as A and I will take this as constant 0. So then my output will be equal to A XOR 0 is always A. So this is acting as buffer. So if I am using XOR gate, then if I am taking 1 as constant for one input, then my output will be complement of the input that I am giving. Okay. Similarly, if I am taking 0 as constant, then my XOR gate acts as buffer. Now let us try to understand for XNOR gate. So one input I am taking 0. So here my output. So output will be A XNOR 0. So in properties we have learned A XNOR 0 is always equal to A bar. So this is inverting buffer. Now let us take constant 1. So I will A XNOR 1. So A XNOR 1 is always A. So it acts as buffer. So when you observe this one, so here if I am taking 1, then it is acting as inverting buffer, but here at 1 it is acting as buffer. Here if I am taking 0, then it is acting as buffer, but if here I am taking 0, it is taking as inverting buffer. Here then we will, this is because XOR is complement of XNOR. So that is one important topic that you need to learn. Now let us try to solve one question for XOR and XOR. A XOR B XOR AB. So if they are asking to simplify this question. Now let us try to simplify this question. So now first we will solve one group. Initially we will take B XOR AB. Now let us try to solve this one. If you apply XOR equation A bar B plus AB bar, then this will be B bar into AB plus AB bar into B. So B bar into B will be 0, and here it will be B of A bar plus B bar. So A bar plus B bar. So that will be equal to A bar B plus B into B bar. That will be equal to 0. Then you will get A bar B. So here you have for now, here A is remaining, and after solving this one you are getting A bar B. Now simply solve this one, you will get answer, that is A into A bar B whole bar plus A bar into A bar B. So when you try to solve this one, you will get here you will get A bar into A bar is A bar. So A bar you will get. Now this one, A of A plus B bar. So that is what you will get, right? A plus B bar. Now A into A is A. Now here we can apply that P into P plus anything formula, then you will get A plus A bar B, then you will get A plus B. So there is one important formula you can derive from this one. If you are given A XOR, let me write it on the page. A XOR B XOR AB, then you will get A as B. And by exchange property of XNOR and XNOR, you can write this one as A plus B, then that will be equal to AB. So by exchange properties of XNOR and XNOR, we can interchange these places. So that is why you will get, if you exchange this one, you will get this equation. I think we have completed everything regarding XOR and XNOR. And tomorrow we will learn about NAND, and then we will complete combinational circuit, and then we will go into this one, what we will call it, combinational and sequential, and then we will go into EDC. So until then, take care, see you in the next video, next session.